Talk about power series and then how to solve ordinary differential equations using power series. This top line here is a power series. Say it's centered at A. It's this infinite sum. If you wrote it out, it would look like this. Notice that the powers of x, or the powers of this quantity x minus a, are non-negative integers. They go from 0 to 1 to 2 and up. We talk about whether a power series converges at a particular point. Mathematically, it means you would set up this partial sum and take the limit as the upper term goes to infinity. If that limit exists, meaning it stays finite for some finite x, particular x sub 1, if it does that, then you say that power series converges at x sub 1. You can see here, it's always going to converge at x equals a. If I set x equals a here, all these terms will be 0 except for the 0th term. 0 to the 0 is 1. So x equals a, you just get this 0 term here. Hopefully it will converge at more than just a. The interval of convergence is the set of all real numbers for which the power series converges. And it turns out the center of the interval of convergence is A itself. The radius of convergence we're always going to pick A equals 0, subsequent use in this course. In that case, the interval of convergence is always from minus r to r, where r is the radius of convergence. We'll talk about how to compute that in a minute. So this is what the interval of convergence will look like when we center it at 0, meaning we set this a to 0. If that radius of convergence is exactly equal to 0, then the interval of convergence is not applicable. By the way, it will converge everywhere within this interval and diverge or not converge everywhere outside this interval. Right at the boundaries, we can't make a statement, so that's why the interval of convergence, we use open parentheses. So if the radius of convergence is 0, the interval of convergence doesn't make sense. We'll just say it's not applicable. The radius of convergence could be infinity, in which case the interval of convergence is the entire real line. So that's the idea of convergence and some of these terms. The radius of convergence, interval of convergence. Any convergent power series defines a function of x. And actually that function will be continuous and continuously differentiable on the interval of convergence. There are some power series that converge to well-known functions like these here, dx, sine and cosine x, etc. But there are other power series that don't converge to anything that's going to look familiar to you. And there's sort of three kind of things that could happen. If you look at this first example, if you wrote it out, it would look like this. That doesn't converge anywhere other than x equals 0. You'll have to take my word for that. So that its radius of convergence is 0, and its IC is not applicable. Here's another example, just simply the sum of x to the n. Wrote it out, it would look like this. And I believe I could convince you that it converges. Well, this infinite sum is this ratio. And it will converge for x's where the absolute power of x, or the absolute value of x, is less than 1. So it has a radius of convergence of 1. IC is minus 1 to 1. Here's another example. Now we're dividing by n factorial. Wrote it out, it would look like this, and actually that converges to e to the x. Its radius of convergence is infinity. So its interval of convergence is the entire real line. We're going to use these things to solve second order differential equations, ordinary differential equations. They'll look like this. We're only going to solve homogeneous differential equations, meaning they sum to 0. So y is a function of x here. So I have y, y prime, and y double prime. These a's are functions of x. So that's what the differential equation will look like that we're going to solve. We're going to talk about the standard form, and we get that just by dividing through by this upfront function of a sub 2. When you do that, you get this. And if I cancel any common factors between these numerators and denominators, I get this standard form. And we use the P and Q to determine lots of things. So the only thing we're going to restrict ourselves in this course. We're only going to solve these second order homogeneous differential equations. And actually all these functions here, these a's, we'll restrict ourselves to polynomials in x. And we're also only going to center our power series at 0 in all cases. One thing we need to talk about is ordinary and singular points. And we talk about the standard form and the P and Q again. And since we're only going to talk about these a's being polynomials, P and Q will be a polynomial in x over another polynomial in x. The singular points are the roots of the denominators of these P and Q. It's where the P and Q blow up. More generally, you need P and Q to be analytic. It's not analytic at a certain x, and that x is a singular point. The roots, since we're dealing only with ratios of polynomials, the roots of the denominator polynomials, P and Q, are the singular points. Any point that is not singular is ordinary. And what we're really going to be especially concerned about, since we're going to center our solutions, our power series at 0, we want to know if 0 is an ordinary point or not. Because we have this theorem. If 0 is an ordinary point, then we can find exactly 2 linearly independent solutions of this ordinary differential equation in the form of a power series centered at 0. And furthermore, we have a way to calculate the radius of convergence. It's the distance of the complex plane from the origin to the nearest singular point. Well, here's an example of that. So here's the ODE, ordinary differential equation, as given. We put it in the standard form, nothing cancels. Both P and Q have the same denominator. So we look for the roots of that. We could use a quadratic formula, and we get these roots. 1 plus or minus I2, a complex number. And those are the only singular points. So is 0 an ordinary point? Well, it's not a singular point, so yes, it is ordinary. And what is the radius of convergence? It's the magnitude. Well, actually, it's the length. Where is this complex number compared to the origin? So I would subtract off 0, which means all I'm doing is taking the magnitude of the complex number. And I do that by taking by using the Pythagorean rule, Pythagorean theorem. It's the real part squared plus the imaginary part squared. Don't square the I. So it's a very simple formula. And then the interval of convergence is this. In this case, it's minus square root of 5 to plus square root. That's where, when we find a solution, that's where the solution will be valid, in that interval. And we'll find exactly 2 linearly independent power series solutions greater than 0. This ordinary differential equation. One last sort of theorem to get out of the way before we get into actually solving the differential equation. This very important property called the identity property. If you have a power series like this is a power series, and you want it to equal 0, the only way that's possible is if each coefficient equals 0. All the coefficients of every power of this quantity x minus a must be 0. And we're always going to center ours at a equals 0. So what we're going to want is every power of x, the coefficient of every power of x is going to have to be 0. You'll see the examples in another recording. And we're going to do this to solve ODEs. So next time, we'll do an example of solving an ODE.